Hello learners, welcome to the next session. In this session, we are going to discuss about quantum annealing. So the outline is what is quantum annealing and concept of quantum annealing, principles how we are going to deal with and challenges. So first, what is quantum annealing? A quantum annealing is a specialized quantum computing technique specially designed to solve optimization problem that affects the quantum states like superposition and tunneling. It encodes the problems into physical quantum system and directly evolved to find the low energy states corresponding to the optimal solution. So the main aim is to identify the low energy states for the optimal solution. Many real world problems such as route optimization, financial modeling and machine learning are to be used, which requires finding the best possible solutions from the enormous possibilities. So we can go for with the number of optimal solution here. Classical computers struggle with these kind of complex optimization problem, but this quantum annealing offer more sufficient approach to solve this kind of approaches. The next is core concept of quantum annealing. The first one is quantum superposition. We know that quantum bits exist in the superposition of state, meaning that they can be both 0 and 1 simultaneously. This allows quantum computers to evaluate multiple solutions at the same time. Next is quantum tunneling. This enables qubits to escape local minima in energy landscape by passing through the barriers instead of climbing over them. So this helps we can directly go to global minimum. Global minimum, that means we are directly get the optimal solutions effectively. Next, adiabatic theorem. This annealing follows adiabatic theorem, which states that the quantum state will remain in its local lowest energy state if changes happen slowly. By gradually, it is having different kind of transition from initial quantum state to problem specific Hamiltonian system naturally evolves towards the optimal solution. So this theorem is based on the state will remain its low energy state when it changes to be happen slowly. Next is the core principle. Quantum foundation uses the qubits that is exist in the superposition, employ the quantum tunneling to escape local minima in energy landscape, and governed by adiabatic theorem, that is slow system evolution preserves ground state solution. So what is the process work here is map optimization task to a problem Hamiltonian, that is energy function, and the best example here we can deal with traveling salesman problem, that is quadratic unconstrained binary optimization formulation. The initialization prepare qubits in a simple transverse field Hamiltonian, that is uniform superposition, and in the annealing evolution gradually transition from initial to problem Hamiltonian over microsecond. Qubits become entangled via programmable couplers that enforces the problem constraint. The last one is measurement. Qubits collapse to classical zeros and one states representing the solution. Here we have a classification of how we are going to deal with quantum and classical annealing. So in terms of parallelism, we can go with that sequential trial states there, explore all states simultaneously. Local minima relies on thermal fluctuation and use quantum tunneling. Energy landscape limited by classical physics, shapes via Hamiltonian interaction. Then hardware, it is a standard weight we are dealing with the CPU and GPU. Here we have a specialized processor or it's also there. That is like a D wave. Computation optimization. Here we can deal with the best solution from the finite set of possibilities while satisfying specific constraint. These problems are widely applicable in logistics, finance, healthcare, and we can apply this for to get the best optimal solution. So key quantum algorithm here is quantum algorithm. Here is quantum approximation optimization algorithm. Operates by alternative between problem specific and mixing unitary operators to iteratively improve the solution. and it encodes the problem into a cost of Hamiltonian when ground state represents the optimal solution. Effective NP hard problem like a max cut and a traveling salesman problem are the best solution here. And variational quantum algorithm, combination of quantum circuits with the classical optimized to minimize the cost function, address the challenges of vanishing gradients through the hyperparameter tuning. And photonic quantum computing use photons to encode and process the combinatorial problems like sampling and gate-based methods demonstrated efficiently in large solutions like a K-snap or a graph coloring also. So quantum simulation here, classical quantum computing solutions also to be there, and the quantum system evolution also to be there, and finally we can directly deal with modeling physical system. So in the case of machine learning, we can go with the quantum support vector machine and quantum principal component analysis can process large data sets more efficiently in the classical method. For faster and computation, we can deal with the quantum approach machine learning algorithms. So for optimization capabilities such as hyperparameter tunneling in ML model or solving different kind of challenges in the traveling salesman problem. And we have a challenges that's also the noise and decoherence, scalability and problem formulation. So the current research thing is non-stochastic, non-stochastic Hamiltonian solutions, error mitigation, hybrid algorithm. Both are to be applied in quantum state. And here we have a simple quantum annealing example is there with the help of D-wave ocean SDK. This is one of the most accessible platform for quantum annealing. Solve a simple quadratic unconstrained binary optimization for a solution f of x comma x2 which is equal to x1 minus x1 of x1 of x1 into x2 plus x2. So here we are implied the packages and define a QUBO problem here, and the thing is to be represented as a binary quadratic model and use a simulator of a sampler here and print the results. Here x and x2 are represent the binary variable and the edge between x1 and x2 has the weight of -2 which indicates the interaction term, that is QC which is equal to QC QU which is equal to -2 times of x1 multiplication of x2. So this is the value here we are represented here. So the output also to be represented x1, x2, energy and number of occurrence. Thank you learners. We will see in the next session. And D waves real quantum annealing to solve the optimization problem with the help of ocean SDK. It uses quantum annealing to solve the problem by evolving the ground state, and great for many optimization problem like job scheduling and the traveling salesman problem. Thank you learners. We will see in the next session.